Hello, I'm David Ullman. I've been designing products and teaching others how to design for over 40 years. Over that time, I've taught a sequential process, one that begins with requirements, moves on to concepts, and then develops the concepts into products. Recently, I've become aware and have begun to use the Scrum framework to manage the design process. Scrum is an Agile framework widely and very successfully used in software design. In this short video, I would like to discuss why this method is not more commonly used to design hardware. It can be, it should be, and is being done with success similar to software. But Scrum for hardware design is more challenging than designing software. These challenges are discussed in more detail in my new book, Scrum for Hardware Design. The obvious question is, why bother? As shown in this table, software organizations who switched to Scrum, an Agile process, dramatically reduced their failed projects, those canceled or never finished. At the same time, they nearly doubled the successful projects, those that came in on time, on budget, and with the functionality the customer wanted. Overall, software organizations, and more recently hardware groups, have seen marked improvement, which is why companies like John Deere, Saab, Lego, Tesla, SpaceX, and many others are applying Scrum methods to their hardware as well as to their software. In no particular order, here are 13 challenges for applying Scrum to hardware. First, modularity is natural in writing code. In hardware, stable fixed interfaces must be consciously designed into the product. Designing from interfaces to parts and assemblies is good design practice, as championed in my text, The Mechanical Design Process. Designing from interfaces helps uncouple complex systems and increases communication between design teams. Scrum encourages this practice. A core practice in Scrum methodology is time-boxed 2 to 4 week sprints. Each sprint ends with a deliverable product. Hardware is difficult to break down this finely, so we're not used to doing this, but there are benefits in that sprints force designing in small, managed increments, which enable better control of the product's evolution. In software, each module of code is an independent function, and new functions can usually be added to existing functions. Not so for hardware. If you try to design hardware with independent functions, the nail clippers, a simple product, gets very complex. In software, form and function are in the same module of code. In hardware, function cuts across many parts and assemblies, each of which may contribute to many different functions. Code is often refactored, rewritten as simpler code. Hardware designers seldom have the opportunity to repeatedly redesign the same product to simplify it. Here, the one-piece nail clipper is a result of many design iterations, an infrequent hardware luxury. Often a software module can be written by anyone on the team. This helps the team balance the workload, with team members swarming to resolve hard issues. On a hardware team, the PC board designer probably cannot help the stress analyst, and vice versa. There is simply more specialization on most hardware design teams than on software teams. At the end of each 2 to 4 week Scrum sprint, the team should have something to demonstrate to the customer. Due to the time needed to model and make hardware, this has historically been impossible in such a short time. Recent modeling and rapid prototype advances are alleviating this, but it is still a great challenge. Scrum is an Agile framework encouraging the rapid ability to make changes. For software, the cost to change code remains fairly constant throughout a project. This is not so for hardware. Commitments to tooling, suppliers, test equipment, and other costs grow as the product matures. Hardware has a broader range of operating conditions than does software. Where code may have to operate on different platforms, hardware may have to operate in widely varying temperature and other conditions. Also, the effects of aging may affect the product's function in life. Software testing is often done with code built into the software product itself. For hardware, there is usually the need for separate test equipment, which will also need to be designed and built. In the example here, the test rig for the Boeing 787 wings was a design project itself. In general, there are more secondary design activities for hardware than for software. As with test equipment, each of these secondary functions require design effort. Software sprints are driven by stories that capture the user's expectation. Virtually all software functionality can be captured in these stories. While hardware must also address the voice of the customer, many specifications are driven by technology and system needs. Methods like QFD, quality function deployment, coupled with stories results in a robust way to drive hardware design. The Scrum methods demand that tasks be completed by the end of each sprint. This forces test-driven design, another hardware design best practice. Test-driven design encourages determining upfront what tests are needed to prove that a task is done. The tests can be simple as setting the goal for a number of concepts sketched, as complex as documenting physical test results, or as visual as demonstrating a prototype. Agile encourages build, measure, learn. While this is a natural sequence, it can lead to premature commitment to build a single solution. Focusing on refining a single alternative can prove to be very wasteful, especially with hardware. Lean design encourages developing multiple alternatives and then culling them as the project progresses. This tension encourages focusing on multiple, parallel, build, measure, learn paths. I've just shown you 13 reasons why Scrum is difficult to apply to hardware design. The infographic shown here is the main figure in the Scrum for Design hardware book. The steps in this figure are designed to stay true to the Agile principles and Scrum process, while at the same time helping you overcome these hardware design challenges. Please contact me if you have any thoughts on these 13 challenges, or if you have comments or questions. Thank you for listening.